we have already talked a little bit previously on double integrals in polar coordinates. So I just want to do some of this with you. So we've learned how to do polar coordinates, what polar coordinates are, what are double integrals in polar coordinates, and how would it change from Cartesian to polar. And in particular, there's that extra factor, conversion factor, that's what people usually forget is put that factor in there. And what I mean is that if you are going to integrate some region that is described in Cartesian coordinates, if you put them in polar coordinates, so this is a region, this is a polar rectangle, it's called, where the radius is going from A to B at all times, and the angle, the possibility for an angle is going between alpha and beta. For example, in that region, if you want to integrate some function over that region, you just do the translation, and very importantly are the translation language, the change of variables equations, which are that x is r cosine theta, that y is r sine theta, that this is just this is not an extra equation that can be deduced from the two above, but it's useful to always remember that r squared is x squared plus y squared, because x squared plus y squared is a quantity that often will show up in expressions, and you can eliminate directly that by substituting by r squared. And then what I was talking about is that when you translate to dr d theta, you go from dx dy to dr d theta, to take into account that we're talking about circular regions, there is an extra factor of r that needs to be included in the conversion so you get the right answer. Okay? So let's do an example where I want to evaluate this double integral in a region R, which let's see what they say. It's in the first quadrant. So the first quadrant is when x and y are positive. It says it's inside the circle of radius 2 in the first quadrant. So if I write 1, 2, 1, 2, then this is the circle of radius 2 in that quadrant. So we're integrating over this region, and this is what we've called R. Okay? And that's the function I'm trying to integrate is over there. So the integral will be, let's first translate the region into polar coordinates. So those are coordinates are theta. If you pick a random point here, I can determine what the length is and what the angle is, what the distance to the origin is, and what is the angle from the x-axis. The possibilities for the radius are what? It's anywhere between 0 and 2, right? Here I have 0, here I have 2, and if you do a line in between, I run over all the possible radii between 0, yes, 0 is less or equal to 0. That's not what I meant. R is between 0 and 2. And what are the bounds for theta? 0 to pi over 2, I just have to see the points, what kind of angles I can get. And here I get angle 0. Here I get angle pi over 2, but I don't have any other angles. So the angle can be anywhere between 0 and pi over 2. So that means that I can translate my integral. Let's call this integral I. I will be the integral. We do integral of theta first, from 0 to pi over 2. You can use Fubini's theorem to actually change the order, but we usually set it up so d theta is first. Then the radius from 0 to 2 of the function. Now I'm going to start translating that x is equal to r cosine theta, so I get r cosine theta plus, and now I see that there is an x squared plus y squared here, so I'm right away going to use my formula that is equal to r squared. R squared. Okay, so I've translated my function into r and thetas, but now that I'm going to write the dr d theta, I have to remember that I have to multiply by the conversion factor. So I have to multiply everything by r. This is another point where people will get, tripped in that you don't have a parenthesis there and you're only multiplying by r the last term in a sum. You have to multiply everything, the entire function, by r. And then that is dr d theta. So that is, we've successfully converted this Cartesian integral into polar coordinates. And now I have to integrate. This function is continuous in that region, so Fubini works here, and I could change the limits of integration. You have to be careful. We will see in a moment that I'm going to talk about type 1 integrals, where the theta, or where the radius depends on the theta, and then that region is different, and to be able to change the limits of integration, you would have to change the type 1 integral into a type 2 integral, which is something we did in the Cartesian coordinates. You can also do that here, but it can get a lot trickier to do it here. Okay? Here, because it's just from a constant to a constant, constant to a constant, that's an integral in a square, and we know from Fubini's theorem that I can switch, and exactly what you said, what you have to do, if you switch these limits of integration, then you have to first integrate with theta, and then r. Yes, the r to convert the dA to dA essentially in the new coordinates, because we are converting circular regions into actual squares. In that conversion, if you try to figure out what is the area of a circular region like this one, it's not just this length by this length. You have to multiply by also, it turns out, by something like this length here. So I have to simplify this. First of all, before I integrate, I'm going to multiply by r. So this is r squared cosine theta plus r cubed dr d theta. And now I can integrate. This will be the integral up to pi over 2 of, now integrating with respect to r, theta is constant. So this is r cubed divided by 3 cosine theta plus r to the 4 divided by 4, that's it, between 0 and 2 d theta. And I can just evaluate at 2 minus the value at 0. The value at 0 will be 0, so all I get is 2 cubed 8 divided by, oh, that's a 3. So this will be 8 divided by 3 cosine theta plus 2 to the 4 is 16 divided by 4 is 4 d theta. So that is the integral that I had. And actually here I just get, so here, now integrate with respect to theta. The integral of cosine is sine, so this is 8/3 of sine theta plus 4 theta between 0 and pi over 2. And then I evaluate, this will be 8/3 sine of pi over 2 plus 4 pi over 2 minus 8/3 sine of 0 plus 4 times 0. Here my 0 is supposed to be 0. What is the sine of pi over 2? 1. So this is 8/3 plus 8, plus just 2. 2 pi. What is the sine of 0? That is 0, so this whole other expression is 0, so I get 8/3 plus 2 pi. All right, so now, as I said, before we had these very nice polar rectangles. The polar rectangles can be made a little bit more tricky if instead of that, I still have the angle going from alpha to beta, but at every angle, I have a different bounds for the radius. So here, alpha is going, or theta is going between two angles, alpha and beta, but the radius goes between two functions of theta. This is what we call a type 1 integral, but in polar coordinates. And we do the same thing we did before. There is going to be, convert the function f into r and theta, multiplied by the conversion factor r. And then what are the limits of integration are going to be in theta is still theta is still going between alpha and beta. And for a given for a given theta, the difference or the bounds for R are between h2 of theta and h1 of theta. So that's why those bounds are now going between h1 and h2. Okay? So let me show you how that works in practice. So for example, this four-leaved clover or rose, this function, this graph, is defined in polar coordinates very nicely by simply r is equal to cosine 2 theta. So I want to find the area. And how do we find areas? Remember that if this is the region, this is my region R, then first of all, let's describe what the region, and then we'll figure out what integral am I trying to do. So the region is, we're going to do it in polar coordinates. Everything that has some sort of like symmetry that looks circular in some sense, it's probably going to be easier to do it in polar than to do it in Cartesian coordinates, especially when the region itself is already given in polar coordinates. So now what it's changing here is the angle. The angles can go, for points in here, the angle goes from minus pi over 4 to pi over 4. So theta is going anywhere from pi over 4 to minus pi over 4. And then what is happening with the radius goes anywhere from 0 to whatever this function is, which depends, the radius depends on the angle. So at this angle, I can go all the way here. At this angle, at 0, I can go all the way here. But at this angle, I actually have to stay at the origin. So here the bounds is that the radius is bounded between 0 and the cosine of 2 theta. Okay? So now I want to just find the area. And remember that to find the area of a region, one of the properties of the double integral is that if you want to find the area of a region, you can just integrate the function 1 with respect to dA. Okay? Because that gives you some sort of cylinder with that shape and height 1, and that cylinder will have volume area of the region times 1. So that's the area of the region, so that's convenient. And now I have to translate it into polar. So now the angles are going between minus pi over 4 to pi over 4. The radius, though, is going from 0 to cosine of 2 theta. The function is 1. So 1 is 1. I don't have to translate x to r cosine theta, y to r cosine theta. There's no x and y's. It's just 1. Perfect. But I do have to multiply 1 by my conversion factor, which is r. And then dr d theta. And here, just about the previous question, r is going from 0 to cosine theta, cosine of 2 theta, and theta is going between these angles. Here, I cannot just switch the limits of integration unless I write what is the theta in terms of the radius. How would we do that? With some arc cosine. Would you prefer to integrate arc cosine or cosine? Cosines, right? So we don't want to do that. We want to keep it in this format so we don't have to deal with our cosine, which probably we could, but let's not tempt fate. All right, so this is the integral that I need to integrate. So let's do it in the next page. It's just the integral of r dr d theta. Okay? Any questions on how I got that integral? So that I need to know for a given, so I need to know one way to figure out what is this is, let me try, that's a good question. So here's how I figure out what is the bound on the radius. What I do is Give me an angle, so theta. Draw the entire line. Okay, draw the entire line that is going through the origin at angle theta, and then figure out all the points of intersection with your graph. So my graph was like this. Okay, so I see that my intersection is actually these points from here to here. Let me do it in another color. The intersection is going to go from here to here. That's not a great color. From here to here. Okay. So I see that I can go from radius 0 all the way to this radius. And this radius, so here the radius is 0. At that point exactly, the radius is exactly cosine of 2 theta. So the bounds on the radius go at any angle. Once I fix the angle, it goes from 0 to cosine 2 theta. Okay? All right, so I'm integrating. Let's see if we can remember. I'm going to integrate from minus pi over 4 to pi over 4 from 0 to cosine of 2 theta r dr d theta. Yeah? All right, so the integral with respect to r is super easy. That is just r squared divided by 2. But I have to evaluate it, unfortunately, of these two functions. And that's going to give me the integral from minus pi over 4, from minus pi over 4 to pi over 4 of cosine squared of 2 theta divided by 2 minus 0 squared divided by 2, so that's just 0. So now I have to integrate that one. And just remember that cosine square, I put it here. The way we integrate a cosine square is by using this double angle formula. So that is the integral from minus pi over 4 to pi over 4. And put instead of cosine 2 theta, there's going to be a 1/2 in front already. And cosine square is 1 plus cosine of twice what I had inside. So this is 4 theta divided by 2 d theta. All right, so this inside here is a 4th plus cosine of 4 theta divided by 4. So the integral of that will be a 4th. The integral is a 4th theta plus the sine of 4 theta has derivative 4 times cosine 4 theta. So actually I need sine of 4 theta divided by 16, right? And then evaluate at pi over 4 minus pi over 4. But you just evaluate at pi over 4, that will have a sine of 4 times pi over, so sine of pi. The sine of pi is 0. So the sine of minus pi is also 0. So I guess I do know what it is. It is going to be 4 pi over 4 plus 4th of pi over 4. So I think it should be 2 pi over 16, so pi over 8. Okay, but I don't care about that number. I care that you see how the integration is done. I care about the number a little bit, but I care more about the steps, especially how we set up the integral, and then how we integrate an iterated integral. Once we've set up the integral, might as well call r equals x, theta equals y again. It's just an integral like we did in the previous chapter, in the previous section of Cartesian integral. It's a conversion to r theta first, and it's a little bit different.